is going to talk about the Poisson maps between character varieties.
So I should start by saying I have known John since 1995 when I spent 3 years in Montreal. And my work was greatly influenced by the paper John wrote with Malcolm Adams and Jacques Hurtubise, as mentioned in Malcolm's talk on Tuesday. So today I am speaking about a paper that is joint with Indranil Biswas and Jacques and Sean Lawton. And it will appear in Journal of Symplectic Geometry. So here is the plan. We will talk about character varieties, Poisson structures, maps between surfaces, construction of Poisson structures, and tapping and gluing. So to begin with, suppose we have two Riemann surfaces, possibly with boundary, and let G be a reductive Lie group or a compact Lie group. Please feel free to interrupt me. I cannot see you because of the way my screen is set up, unfortunately.
Okay, we will interrupt you.
So please interrupt me if necessary. That will also stop me from going too fast. So X of sigma is just representations from the fundamental group of sigma into the group G up to conjugation. These spaces are Poisson manifolds. If the boundary of sigma is empty, then, as was shown by Attia and Bott, also Bill Goldman, these character varieties are symplectic, in fact. So if sigma 1 is included into sigma 2, let's let F be the inclusion map. And then there is a map from the character variety of sigma 2 to the character variety of sigma 1, which just comes from basically from pushing forward the fundamental group. So this is representations of the fundamental group. Okay, so far, strictly speaking, this is a map from representations of the sigma fundamental group of sigma 2 into G into representations of fundamental group of sigma 1 into G. But this map is equivariant with respect to conjugation by an element of G, and so it does go to give you a map of character varieties. Lisa,
is it real surfaces, two surfaces, or complex surfaces?
Oh, I meant Riemann surfaces. So yes, they are Riemann surfaces. So
and they're compact.
Yeah, they could be compact with boundary.
Okay.
Or compact. But they're certainly real two-dimensional surfaces. I am not talking about complex surfaces. Okay. Oops. So I'll denote for a surface of genus G with n boundary components, I'll write this as sigma sub ng. And sometimes I write the character variety as x sub ng. And our objective is to show that the map phi is a Poisson map. I think I was apprehensive to call these Riemann surfaces because what I'm doing does not really depend on the complex structure.
But they're oriented.
I am talking about real two-dimensional surfaces, not about complex surfaces.
With orientation.
Yes. Oriented surfaces. Okay. So there are a few general results about character varieties. One is that so if the surfaces have the same Euler characteristic, and so sigma 1 and sigma 2 have the same Euler characteristic, and both surfaces have at least one boundary component, or both surfaces have no boundary components, both are closed. In that case, the two character varieties are isomorphic. I won't spend too long on this, or maybe I'll come back to it. Basically, case by case. So,
Lisa, just a bit confused, but are these two surfaces supposed to be one inside the other? Or
okay, so I did introduce that you have an inclusion map from sigma 1 into sigma 2.
oh, it's a map. Okay, okay.
Well, I defined so F from
Okay.
from sigma 1 to sigma 2
They're not
inclusion.
Okay.
Later that will be weakened. So there will be other maps that are not just inclusion maps. But so far I had introduced an inclusion map. So this is breaks down into cases. First, the case where there's at least one boundary component. Second, both surfaces are closed. And third case, one is closed and the other isn't. So in the first case, both fundamental groups are free groups and they have the same rank, so the character varieties are isomorphic. Surfaces don't need to be homeomorphic, but they must be homotopy equivalent. In the second case, the fact that the Euler characteristics are equal means that the surfaces are homeomorphic, so the fundamental groups are isomorphic. And so also the character varieties are isomorphic. In the third case, you get rapidly to contradiction. So that can't happen. Other characteristics are equal, but the character varieties are not isomorphic. And in this case, the character varieties are not homeomorphic. Okay, so finally, if you have two character varieties that are isomorphic, then the corresponding surfaces, there's an echo somewhere.
I think, yes.
then the corresponding surfaces have the same Euler characteristic, and either both surfaces are closed, no boundary, or neither surface is closed. This is basically because if the two character varieties are isomorphic, their dimensions are equal. And if one surface has a non-empty boundary and the other doesn't, then let's introduce K to be the maximal compact of G. Then this thing is not homotopy equivalent to the retraction to the character variety into K, as long as the genus is bigger than or equal to 2. So either both surfaces are closed or neither is. This implies that the surfaces have the same Euler characteristic because the dimension of the character variety is the product of the Euler characteristic and the dimension of G, plus a term that depends only on G and not on the surface. So that's basically how that goes. So I will pass to just mention that if two character varieties are isomorphic, it does not always follow that the fundamental groups are isomorphic. There's a simple counterexample, Z2 and Z3. These both have character varieties that are 2 points, although these groups are not isomorphic. So wanting to get to Poisson structures. So in local complex coordinates, the bivector of the character variety can be written like this. The Aij are just functions of the complex coordinates Zi. Let's use notation where alpha and beta are base loops in the surface sigma 1. So they give rise to elements bracket alpha and bracket beta in the fundamental groups. Without loss of generality, these base loops intersect in transverse double points. And let's write alpha intersection beta just as the set of double point intersections. Is there a question? Is there a question?
I don't understand. Is this a real Poisson structure?
Yes. You mean why am I using complex coordinates?
So I expected that you will use D over D Z J bar Z bar for one of them. So okay. So.
No, this is actually.
So it's a complex Poisson structure.
It is, yes. The character varieties are complex. Mm-hmm. So it's possible to write in complex coordinates.
So those AJs are not just functions, but they're also
the AJs are functions. The AIJs are functions of the Zs.
Holomorphic.
I don't think the AIJs have to be holomorphic.
Maybe.
Any case, let's see how they are produced. I'll write the intersection number of the double points and write alpha sub p as this is the same notation as alpha, except we're introducing the base point p. So if script R is a representation of the fundamental group, then we write f sub alpha of R. This is just here. F is a function from G. Yeah, this would not have to be a complex function. Could be a real function. Could be something like real part of trace. Or. So you're evaluating R of alpha. You're evaluating F at R of alpha, which is a point in G. So this is a notation. So the bracket is an adjoint invariant inner product on the Lie algebra. Basically, it's the killing form. And this object was developed by Bill Goldman. So associated to another function, little f, on the Lie group. Goldman used basically the trace or the real part of the trace. Basically, you start with some function defined on the group, and you associate an element of the Lie algebra.
Is this symplectic form unique?
The symplectic form on the symplectic form on for closed manifolds, the symplectic form. Okay, so closed symplectic form is due to your bot. Would be around. And as far as I know, the symplectic form on the character variety is unique up to multiplication by a constant. So this form, this symplectic form on the character variety does represent this is the form whose cohomology class is the first Chern class of the pre-quantum line bundle of those moduli spaces. And as far as I know the only non-uniqueness would be actually because also it is, yeah, you want to multiply it by an integer because it is first Chern class. Its de Rham cohomology class is the first Chern class. So you're probably wondering why. So the ingredients in this construction involve you are choosing a function, the function little f, and you're also choosing the killing form, which could be multiplied by a constant scalar.
You're assuming that G is semi-simple?
UN is not semi-simple.
Yeah, G.
Yeah, right. G equals SUN is semi-simple. I mentioned all. UN is not semi-simple. I don't think I'm assuming that G is I don't think at this point that I am assuming that G is semi-simple. It's certainly possible to do parts of these constructions for groups that are not semi-simple.
The carton form be degenerate.
Sorry?
The carton form, the carton form could be degenerate.
Yes, I see what you're. Yes, so. Yes, it might be if you were using something like U1 to be something that was not semi-simple. But there are cases where we are restricting to semi-simple. Okay, so at this point, just for an example, this capital F takes values in the Lie algebra of G, and in the case for little f is the real part of the trace, the capital F is A minus A inverse, and this does take values in the Lie algebra of G. So still looking at R is a homomorphism from pi to G, Poisson bracket. This definition is due to Goldman. Actually, in some cases when it's due to Lawton and Sikora. We'll get to that later on. But in the case where the surface is closed, it was first defined by Goldman, and you sum over the intersection points of alpha and beta, and you take the inner product of R of alpha, F of R of alpha, and G of R of beta, where capital F is associated to little f and capital G is associated to little g in the way I described above. Yes, so the Poisson bracket, Poisson bivector was computed for G equals SL2C by Poisson bracket was defined by Goldman. This in the case where no boundary and genus bigger than or equal to 2. And for no boundary, genus 1 by his student Adam Sikora, and by Sean Lawton in the case when there are boundary components. For SL2C, Goldman also found the bivector for genus 0 and 4 boundary components, and also the torus genus 1 with 2 boundary components. So let's look at a situation where Q from sigma 1 to sigma 2 is a continuous map. We're no longer restricting to just inclusion maps. Then there's an induced homomorphism of fundamental groups and a continuous map from one set of representations to the other. And this descends to character varieties. So this gives you a map from X of sigma 2 to X of sigma 1. And Goldman proved that, so now
Lisa, I have a question. When you say they found the Poisson bivector, right?
Yeah.
So
that's the one that I was talking about on the previous slide.
So they you have to commit to some set of coordinates to do that, I assume.
The coordinates. Well, here you write it down for specific choices of curves alpha and beta.
Okay.
And otherwise, the choices are, as I described before. You're choosing the killing form, and you're choosing the input involves functions f and beta. Those are f and g. Those are just functions from those were these functions from the group to complex numbers or the real numbers. And then for any such function, you get another function which is into the Lie algebra. So I think all that I'm choosing here is the killing form.
Okay, thank you.
Okay. All right, I think I skipped something. Yes, so if Q is a map of compact orientable surfaces, Goldman required that the map preserve transversality of base loops and preserve double points. And under those hypotheses, the map Q upper star from coordinate rings on the character varieties, that is a morphism of Poisson algebras if Q preserves the orientation, and it's an anti-Poisson morphism if Q reverses the orientations. So now let us assume that the surface is an open, smooth manifold instead of a manifold with boundary. So I'm deviating from my assumption that things were compact. And let's assume that either G is a compact group or it's a reductive group, the complexification of a compact Lie group. We fix a base point, and a homomorphism from the fundamental group of the surface to G is called reductive if the Zariski closure of its image in G is a reductive subgroup. This is always satisfied if the group is actually compact. So let G be a Lie group. Then I introduced X and G. This is the quotient up to conjugation of the space of reductive homomorphisms of the fundamental group of a surface of genus G and boundary components into the group. So I'll write a G connection as a smooth principal G bundle on the surface sigma 1, which is equipped with a connection. And if E is a vector bundle over sigma 1, associated to E will be a vector bundle over sigma 1, which is associated to this principal G bundle through the adjoint representation. Then Poincare duality tells us that the tangent space of the character variety is the compactly supported first cohomology of sigma with values in E. So then there is a natural homomorphism from the cotangent bundle of sigma to the tangent bundle of sigma, or equivalently a two form on the character variety. That's basically what we've already constructed. This is given by taking the inner product of a one form on sigma with a compactly supported one form on sigma to form a compactly supported two form on sigma. And then you integrate that over the surface. We can denote this homomorphism by capital theta. Equivalently, you think of theta as a two form on X. If sigma is a compact oriented surface, then the two form theta coincides with the symplectic structure constructed by Atiyah-Bott and Goldman, which I mentioned already. Any questions to this point?
No.
So if sigma 1 is embedded as a connected open subset of sigma 2, then the restriction map from sigma 2 to sigma 1 gives you a map from the sigma 2 character variety to the sigma 1 character variety. And we have a map which I'll call beta, which goes from the first cohomology of sigma 2 to the first cohomology of sigma 1. This just comes from restriction. And another map which goes in the other direction for compactly supported cohomology. So this map, beta, is just the differential of the map phi. Results from pulling back one forms under the inclusion map from sigma 1 to sigma 2. There's another map. The other map, gamma, is the dual map to d phi. And it results from pushing forward from sigma 1 to sigma 2 under the inclusion map. Remember, here we're working with compactly supported forms. So to check that the map phi is Poisson, to check that a map F between two Poisson manifolds is Poisson, you just have to check if the Poisson structure on A is written as theta A, and the Poisson structure on B is written as theta B. You just have to check that this equation holds involving the differentials of F. So that is how we verify that. So if we had a covering map from sigma 1 to sigma 2 could be a ramified covering map, then we denote by psi the map from the sigma 2 character variety to sigma 1 character variety that is given by pushing forward the fundamental group under phi, little phi, from sigma 1 to sigma 2. And we check using this criterion that the map psi is in fact Poisson. This uses the fact that deep psi sends a cohomology class to its pullback under phi. And the map dual to d phi sends a compactly supported one form to the sum of its pullbacks over the inverse image points under the map phi. This form is also compactly supported. Then we have to use this criterion. So I'll describe what I mean by capping surfaces. So if sigma 1 is a two-manifold with boundary, let's suppose that sigma 2 is a two-manifold obtained by capping the boundary components as described below. So phi is, as in the previous section, the map from the character variety of sigma 2, the capped surface, to the character variety of sigma 1. Of course, now sigma 1 is, the map from sigma 1 to sigma 2 is an inclusion map. So in the first case, you would have capping with disks. So you have two boundary components here, for example, and you cap them off with, cap each of them with a disk. We could also cap this surface with a cylinder, gluing the two boundary components of the cylinder to two boundary components of the surface, like so. This produces a surface with two less boundary components, and the genus is greater by 1. These two character varieties have the same dimension. You could cap with a k-hold sphere if there are k boundary components. So the resulting surface has genus k-1 higher. So in this case, we start off with something with genus 1 and 3 boundary components. You cap it off with a 3-hold sphere. What you get has genus 3 and no boundary components. This map, corresponding map on character varieties, is not surjective. You can cap off one boundary component with a genus 1 curve with one boundary component. So that looks like so. If G is semi-simple, then that map of character varieties is surjective. But that would not be the case if it's not semi-simple. Another example, capping a surface with n boundary components with an n-punctured genus 1 curve. So in that case, the map is surjective, and it is a Poisson map. So I wanted to describe how some of these results appear also in the work of Alexeyev, Malkin, and Meinrenken on Q Hamiltonian spaces. So we introduce what's called the double. This is so two different notations, which the spaces are the same, but the group actions are different. So here you have an action of G cross G. And here, again, the space is still G cross G, and you're really using the diagonal G action. This is called the internal fusion of the double. So this is how the action of G cross G looks on the double. Left multiplication and right multiplication by the inverse on the other side, and right multiplication for G2, and then left multiplication for the other. There is a 2-form on the double, which is constructed from the Moret-Cartan form. So little theta represents the Moret-Cartan form for left multiplication, left Moret-Cartan form, and theta bar is the right one. So theta is often written if you write your group variable as A, you'd write theta as A inverse dA. So these spaces have a two form, which is not closed and also not non-degenerate, but it accomplishes some of this. It has some other properties which do the same job and to fulfill symplectic reduction. That is the quasi-Hamiltonian formalism introduced by these authors. So the two form on the internal fusion is just basically wedge product of the Moiré-Cartan forms, left and right, pulled back by A and B. These are is their notation for the double. Wrote two forms as A and B. So yes, this two form is for the double with the G cross G action, and this is the two form for the double with the G action only. And Q Hamiltonian space, which is a product of R copies of the double and G copies of the internally fused double. So this is just 2G plus 2R copies of G, and it has an action of G to the R plus 1, written like so. So it's left multiplication or right multiplication on some of the variables. The UV variables correspond to the double, and the AB variables correspond to the internally fused double. So this space is equipped with a two form, which plays the role of symplectic form, and with maps that are called moment maps, but don't satisfy all the criteria of moment maps, but enough to allow one to define an analog of symplectic reduction. So this is what they look like at these values. Introduce the notation bracket to represent commutator. So A, B, A inverse, B inverse. This is for a group. Yeah, it should be for group H or G. It should be G. So to form a Poisson manifold by gluing two boundary components of a connected surface, we set the moment maps in the sense of Alexeyev, Malkin, Meinranken, corresponding to these two components to be equal, and then take the quotient by the diagonal action of the group. So that is basically the same as capping with a cylinder, as described earlier. To form a Poisson manifold by gluing together boundary components of two different surfaces, we set the moment maps of the two quasi-Hamiltonian spaces to be equal, and then take the quotient by the diagonal action of the group. This procedure can be iterated, and if all the boundary components are glued together, then we recover a symplectic manifold. So this gives an explanation partially where the capping fits in. some of this can also be interpreted in terms of extended moduli spaces, which I introduced in 1994. These are finite dimensional spaces equipped with a symplectic form and a Hamiltonian action of a group. To form a character variety corresponding to a surface that you obtain by gluing together two boundary components of a connected surface, we take the symplectic quotient of the extended moduli space by the diagonal action corresponding to those two components. And if you're taking, so that's an analog of what's happening in this picture. If you have two different surfaces, as in this picture, then this is, you form a character variety corresponding to a surface obtained by gluing together two boundary components of two different surfaces. Then we take the symplectic quotient of the diagonal action of G on the product of the two extended moduli spaces. This involves setting the two moment maps equal and then taking the quotient. So the extended moduli space more or less has the same purpose as the quasi-Hamiltonian spaces, except that the extended moduli space is non-compact and singular, which the quasi-Hamiltonian spaces are not. So finally, actually, the first thing I should go over the references that I mentioned earlier. And there's one more page. And finally, happy birthday, John. Are there questions?
It's your unbirthday.
Thank you.
Thank you, Lisa. So, are there questions from audience or from Zoom audience?
I mean, John asked at some point, what is the condition on the group, whether it's semi-simple or reductive?
Yes.
So well, what I want to ask, certainly for the definition of this quasi-Hamiltonian manifolds, it's enough to have some invariant non-degenerate bilinear form. Maybe the structure of the quotient spaces is not so good. I mean, is it? So my question is it enough to just have an invariant non-degenerate bilinear form, for which you don't need reductive or semi-simple?
Okay. The Alexeyev Malkin Meinrinken's definition is not something that we really used. So their hypotheses may be different from ours. I think that they were using semi-simple and also simply connected.
In the original paper, I think they used some compact groups.
Compact groups, yes. Yes, that's true. I'm not sure that they generalized to non-compact groups. I mean, most of the time we were using reductive groups when reductive group is a complexification of a compact group. So I'm not sure that what we were doing was more general than what they were doing.
I mean, it uses cut product.
Yeah.
So maybe the sort of arbitrary form might not. I mean, for an arbitrary group, it might be a little bit difficult.
Well, I think for to define this quasi-Hamiltonian manifolds, this double internal fused double, just need the molar Cartan forms and the pairing. But maybe the quotient spaces, the topology, they will not be good with manifolds. I think I suspect that is the trouble. The nature of the quotient spaces, if the group is not reductive, say. But it still exists. I mean, it's an nasty space.
There's a little internal debate here. I'm not sure between Isaac and the rest of them. Are there other questions or comments? Well, in that case, let us thank Lisa for the talk.
Thank you very much.